So our paper is using galaxy clustering and weak lensing data from the first 3 years of observations by the Dark Energy Survey. And we're using those measurements to constrain several beyond Lambda CDM cosmological models. So this includes dynamic dark energy, it includes curvature, sterile neutrinos, modified gravity, and some another approach to probing structure growth, which we'll detail later. So this is sort of a follow-on to the previous DES cosmology results from weak lensing and galaxy clustering, which constrained Lambda and WCDM.
Weak gravitational lensing is very powerful at adding information on the effective mass of sterile massive neutrinos, which will help understand what is dark matter, basically. The second thing is that we show constraints on a test of gravity with only low redshift probes without the cosmic microwave background. And more generally, we are able to reproduce different results on those extended models using different probes. So using the cosmic microwave background, which is the early universe, or our data, which is the late universe, and we are able to kind of constrain the same model using these two very different data. The third thing that's very important is that we need to develop the modeling tools to be able to test those models with the future data that we will get from Rubin, Euclid, and the Raman telescope. So those are the three main messages that we want to convey.
Many of the viewers are likely familiar with the idea that by probing the evolution of structure in the universe and the imprints it makes, in the early universe on the CMB observables, and in the late universe on the evolution of large-scale structure, the properties and evolution of that structure are sensitive to all kinds of fundamental physics in our universe. And so by measuring the evolution of structure, you can test different variations to the physics describing, for example, gravity or the contents of the universe or the various forces governing their interactions. Yeah, we work with a galaxy survey because while our models, whether we're working from simulations or Boltzmann code or your favorite modeling method, we can predict the evolution of structure for the total matter, namely the dark matter. We don't see that, we see galaxies. And so DES and other galaxy surveys work by leveraging the imaging of galaxies, both their positions and distortions of their shapes due to weak gravitational lensing, to give us precise measurements of how big matter fluctuations in the universe are. And I guess Agnes will speak to the survey specifically and sort of why we picked the models we look at.
Yes, so we are using the data from the Dark Energy Survey, which used the DCAM camera on the Blanco 4 meter in Chile. And one of the properties of this survey is that it imaged 10% of the sky in 5 optical bands. And we are, Jessie and I, members of the large international DES collaboration that works really hard to extract cosmology from this data. And so why are we doing this now? So a few years ago, we released the cosmology from the first year of observation, which are released on those papers. And we actually, between the first year of observation and the 3 years of observation, we made a huge step because we have observation over 3 times more sky, and so the full 10% of the sky. We measure properties of 12 times more galaxies, which end up forming the largest shape catalog to date for weak gravitational lensing with 100 million galaxies. And in the end, the data that we used, their signal to noise ratio is twice as better as for the first year of observation. So it seems like it's a very powerful set of data to test the Lambda CDM model. So yeah, we use those precise data to test the Lambda CDM model. And the first step that we make is to measure omega m and S8. And S8 is this combination of sigma 8 and omega m. And we were, first of all, thanks to all the effort that we put in, we were able to measure S8 with a precision of 4%. And this measurement is shown in gray here in this plot, which was released last year. So we compare the result on S8 coming from our data with constraints coming from the cosmic microwave background measured by the Planck satellites, which is here in green. And so we see that there is more or less agreement between the two, although there is still this sort of like lower value of S8 measured by DES, which is kind of consistent with what we've seen with other lensing survey. But for us, we wanted to go beyond that. On top of, like just comparing in Lambda CDM what our results compared to Planck, we also wanted to answer directly some questions about the universe. So what is dark energy? What are the laws of gravity on cosmological scales? What is dark matter? Is the universe really flat? So basically it was choosing which model to look at was a balance between what the community is interested in. Like I think a lot of people, cosmologists wants to know what is the value of W naught and WA. So like asking the question, is dark energy dynamic or not? And it was also a balance with what the dark energy survey data can add. So like what are the models where we can really add something? So we gathered a team of people in the DES collaboration like 4 years ago, actually. So that was a many-year effort. And just wanted to say that many of the people in this team are early career scientists, and we gathered to try to use this data and really kind of build on all the efforts from the DES collaboration to constrain those models. So specifically, we looked at a time-dependent dark energy equation of state, which we parameterized by W naught and WA. So W naught is the value of the equation of state today, and WA is its dependence with time. We also looked at omega k, so if to measure the spatial curvature. We looked at massive sterile neutrino, which we parameterized by N effective and M effective, which we're gonna come back to later. We also do like a phenomenological test of gravity on cosmological scales using the sigma mu parameterization, which we will also develop later on. And we also measured sigma 8 in different redshift bin to test if there is any deviation from what we expect in Lambda CDM. So basically our approach is that we take the Lambda CDM analysis as our baseline, and we add these extra parameters, and we have to take into account their impact on the DES data. And we take, as we did in Lambda CDM, a Bayesian analysis where we need to sample this likelihood here that we're gonna talk about afterwards. But so basically to estimate these extended parameters and the tension between extended models and Lambda CDM, we run Monte Carlo Markov chains, varying a lot of parameters. So we vary the 6 baseline cosmological parameters and 22 nuisance parameters for like astrophysical effects and systematic uncertainties, and also our Beyond-ΛCDM CDM parameters. And in the end, we ended up running 700 Monte Carlo Markov chains. So you can understand why it took us like 4 years to complete this. Um, so for people who want to know, we use the polychord sampler to do the parameter estimation because we validated it in a paper, and we used an analytic covariance matrix. And we will also show results using external data, so from the CMB, from Planck. We also use supernovae from Pantheon, and also bionic acoustic oscillation and redshift space distortion from EBOS and MGS. So yeah, so our data, as Jessie was mentioning before, are 3 different sets of 2-point correlation functions. So we correlate the shape of galaxies to have information about the weak gravitational lensing effects. And we also correlate the position of galaxies. So we first build one 2-point correlation function, which is a cosmic shear, and that gives you so that gives you directly information about the distribution of matter and its evolution between us and the background galaxy, those source galaxies. Then when we correlate the position of galaxies, we are trying to trace directly the dark matter structures. So we have access to the matter power spectrum with a bias, a galaxy bias square. And then we also measure the correlation of background, like the tangential shear of background galaxies around foreground galaxies. And that gives you access to the matter power spectrum with one factor of the galaxy bias. So when you combine all of them, you can extract a lot of information and break degeneracies. So for the source galaxies, we used the meta-calibration algorithm, and the galaxies are in 4 different redshift bins, which are shown here in the bottom left. And for the lens galaxies, we use the maglim sample in 4 redshift bins. So you might see here at the bottom right that there are actually 6 curves, there are 6 redshift bins, but in the Lambda CDM analysis, we realized that there was a mismatch between galaxy-galaxy lensing and clustering. And this mismatch was even higher for high redshift bins. And we decided in our analysis to just remove those 2 redshift bins because we think this mismatch is due to something related to the data and not about new physics. So we thought we would mention it here because it might be a question people have. Yes, so actually now most of our effort in this paper is actually in the modeling, because now when we sample the likelihoods to estimate the parameters, we need to basically predict the signal we expect in each of those models. And we want to model the weak lensing and clustering accurately enough to do this parameter estimation. So one main ingredient in the modeling is the matter power spectrum, because that's what will source the weak lensing and clustering signal. And for that we use CAMP, and in test of gravity we use MGCAMP. One important point is to describe the nonlinear regime of the matter power spectrum. We use halophytes. And so then we project the matter power spectrum into cosmic shear, galaxy-galaxy lensing, clustering. But we also need to add contribution from the intrinsic alignments, which is the alignment of galaxies that are forming in the same gravitational potential. And so they will tend to correlate between each other, but it won't be cosmic shear. So we need to take that into account. And we use for that the nonlinear alignments model. Taking into account basically the tidal alignment of galaxies. And then to relate dark matter to galaxies, we use a linear galaxy bias. And we also take into account magnification. because some galaxy will be magnified by weak lensing, so they will appear, like more galaxies will appear in your catalog of galaxies, so you need to take that into account, and we do here. And a big important point as well is that we have those great measurements of those three sets of correlation function, but we actually remove quite a bit of those data points at small angular scales, because that's where we don't trust our modeling anymore, because there is bionic physics happening that we don't model in DES, at least in this analysis. And there is also the galaxy bias starts to be nonlinear, and we don't model that either. So that will be an important point we will come back to.
So Agnes has done a really nice job kind of setting up what the data we're working with and how we approach the analysis. So I'm going to kick off a sort of mini whirlwind tour through some of the results in the paper. This is quite a big paper. There's a lot going on in here, so we're going to try and highlight a few things, starting with dynamical dark energy, since, you know, our survey name is the Dark Energy Survey, so gotta have this in here. And the results from DES alone are shown with the blue contour in the upper left panel. The red contour shows the CMB measurement alone, and the black contour shows the combination of all data, whereas the purple contour is DES plus other low redshift probes. So that's BAO, RSD, and supernova data. I think the key point to take away from these plots, and I would say the lower right plot is just the same results with a couple extra contours zoomed in to show the tighter constraints. And the main thing to take away here is that everything's consistent with W naught equals -1, WA equals 0, so with cosmological constant dark energy. And a thing that we wanted to highlight, especially looking at this plot on the lower right, is you can take away different data sets that contribute to these constraints, and things stay fairly consistent. So like the purple contour is if you take away the CMB information, the pink contour is if you take out the DES and RSD, like low redshift structure growth information, and it kind of gives you a sense of how much, or really how stable this result is with these sort of complementary pieces of info. All right, so that's our dynamic dark energy model. We also looked at curvature. So again, the color scheme is going to be consistent through all of these plots. So the main thing to note here is that the blue DES 3x2 point, so galaxy clustering and weak lensing constraints, don't on their own constrain omega k very well. But if you combine those measurements with the other low redshift BAO supernova RSD measurements, they can tighten the constraint you can get on omega k without including any CMB information at all by about 20%. So this is another case where, while the galaxy clustering and weak lensing data doesn't do a ton here on its own, and maybe compared to the combination of all external data doesn't really tighten constraints, it does allow for some extra robustness and redundancy at looking at how these constraints change when you leave in or out different data sets. The main outline here is that the constraints seem to be compatible with flatness. And then as Agnes alluded to earlier, modeling limitations is something that we ran into with this model. So for curved universes, there have actually been in the past couple of weeks a couple interesting papers out moving on this, but there hasn't been in the past a ton of validated modeling for whether standard tools used for nonlinear power spectrum modeling can be used for curvature. And then also we use our measurements are accurate enough that it's a first for this kind of survey, where when we do projections from the 3D matter power spectrum to 2D correlations of galaxies on the sky, we can't use the pretty commonly used Limber approximation when we're computing galaxy clustering. And it's new for DES that our data is at a precision where we need to do that. And so future surveys will as well. And this is not validated for non-zero curvature. So we have to do really conservative scale cuts here, where we throw out over half of the data points that are used in the Lambda CDM analysis. And so that's just something to highlight here of a limitation that as data get more constraining, that's going to be even more challenging if the modeling doesn't develop. And then the next model that we'll discuss is a parameterization of massive sterile neutrinos. So this is if there's some species of neutrino that doesn't interact in the same way or interacts more weakly with that in the active neutrinos, so decoupled sometime in the earlier universe, we can look for how that impacts large-scale structure. So if you're thinking about what the physics of this is, it's roughly like these things act like they suppress the power spectrum at small scales, similarly to what you'd expect for massive neutrinos, but you have another dial in this n-effective parameter, which it's the same n-effective parameter that if you're looking at extra relativistic species, you can change matter radiation equality. When you look at how that impacts the matter power spectrum, basically going to smaller delta n effective, so excess n effective from what you'd expect from the standard model, that'll cool down your sterile neutrinos and move your free streaming scale to higher K or smaller length scales. Um, and so that's sort of a hint that, getting some large scale structure data like the measurements that DES allows can be really helpful for constraining this. And here, individual measurements from either the CMB or DES aren't particularly interesting in and of themselves, but together you have the synergy where the CMB is very good at constraining N effective, which is the horizontal axis on this plot, and large-scale structure data, DES, is very good at helping pinning down M effective and stronger when you can combine the BAO and supernova data to help break some degeneracies. And so the black contour in this plot is that combination of all the data together. And we find, given this constraint and somewhat sensitive to how we choose to set priors on N effective, we get a 95% upper bound on this M effective parameter, which is basically like how the sterile neutrino contributes to omega matter at 0.2 eV. And just to emphasize that this is something where DES really adds information compared to a similar analysis in the Planck 2018 cosmology constraints. This is a factor of 3 tighter, so this is pushing things forward. It's like this is another place where we ran into a limitation of our modeling tools. So modeling nonlinear power spectrum growth or nonlinear structure growth when you include these kind of light relics, or even when you include just active neutrinos, is kind of an active area of investigation with people doing n-body simulations and studying them and working on the perturbation theory. So this is something that people out there are actively working on. We didn't have tools on hand to model nonlinear structure for this model, so we only have linear modeling here and therefore had to do some really conservative scale cuts again. So we've got this, advancement in the precision of this kind of constraints, and this is using less than like something like half of the data points that we use for the Lambda CDM analysis. So this is something where with modeling advances, there's potential for doing even better with data we already have in hand.
So we also did test of gravity. So the approach we took here was to do what has been done several times in the past, but we think it's actually like a very nice parameterization. So we applied it here again. And the idea is to change, instead of like changing the Einstein equation of general relativity, we modify the way the light reacts to gravity and the way matter reacts to gravity. So what that means is that here on the top, the Newtonian potential will be modified by this function mu, and the lensing by this function sigma. And those functions depend on time and scale, but we decide to just consider a time dependence as omega lambda. And what we want to measure is sigma naught and mu naught, so the value of sigma and mu today. And this is very nice for us because sigma will change the lensing signal, basically. So with the weak lensing measurements we have, we should be able to measure sigma naught. And that's what we did. So, and even I think one main takeaway from this plot that shows the result on sigma naught and mu naught as well as ACE8, because ACE8 also change the amplitude of lensing. So we have a degeneracy between sigma naught and S8. So it's really nice to see this degeneracy like that. Um, one one of the few takeaways is that we make a measurement of sigma naught with only low redshift measurements, so with DES, which is in blue, and RSD in green, to which constrains mu naught, because as we see, mu naught modifies the Newtonian potential. And that's exactly why this model was introduced, because you can really use RSD and weak lensing, which are like orthogonal in sigma and mu, and you can combine them to get nice tight constraints. And that's what we have here in purple. And another interesting thing that we see is that there seems to be a tension between Planck in red and this low redshift measurement in purple. So this tension, again, like for omega k, it's still below 3 sigma, so we are able to combine all of that to get the black contours, so combining all of the data. And we see that sigma naught and mu naught are consistent with 0, which corresponds to general relativity. So no detection of deviation from GR, but still very interesting slight tension and like a nice step forward, combining the best data that we have right now. So next, we also looked at another model that tests for the non-standard growth of structures. And here the idea is to measure sigma 8, or the amplitude of matter fluctuation in redshift bins. So what we did is rescale the matter power spectrum by a parameter, AI, in each of the length redshift bins. And we kind of reframe those AI, which are kind of the equivalent of the standard AS. We rescale them in terms of sigma 8, which is shown here in this plot. And this is very exciting because usually we see those kind of plots coming from RSD experiments, like probably EBOS or other experiments have those type of plots. And here we're doing that, but for a photometric survey with weak lensing. And in blue, again, it's a result from DES alone. And then we add other experiments and to get the black data points. So we see that it's consistent with Lambda CDM, which is this shaded area. Although at the highest redshift bin, there seems to be like a small deviation, but nothing to be worried about, but still something maybe interesting to look at. One important thing is the way we model our uncertainties on the photometric redshift will impact the results on sigma 8 in redshift bins. That means when we have an approach to model photometric redshift, we also kind of have to think about how it impacts our results in beyond Lambda CDM models, because actually it can have an impact. And this impact is less when we combine, like our constraints are more robust when we combine with external data. But that was an interesting like takeaway from this, and again, more work to be done there.
All right, so that's sort of a quick overview of results for several of the individual models we looked at. Sort of, there are a couple key things that we might be interested in looking at, you know, given the amalgamation of all those models together. One is, you know, let's look at some model comparison statistics and evaluate, is there any preference for any of these added parameters as opposed to the more minimal Lambda CDM model? And so this busy plot is actually a subset of a larger busy plot in our paper. So there's a bunch of different model comparison statistics out there in the literature. People have different preferences. You can get different insight from different ones. So we've opted to report a bunch of them. So how to read this plot is that each panel is a different model comparison statistic. Each row is a different model comparison. And for all of these all of the panels, things are set up so that points further to the left indicate more tension with the Lambda CDM, or whatever the simpler model is. The three model comparison statistics we look at is the Bayesian evidence ratio, log R, the leftmost panel. We also look at, on the right side, delta chi-squared, so change in the goodness of fit of the best fit point of the two chains, compared to the number of added parameters. So those are things that people are probably most likely to be familiar with. The middle panel is a statistic based on another Bayesian quantity called suspiciousness. So suspiciousness is something that was initially introduced mainly for assessing tension between data sets that kind of takes out dependence on the size of flat priors. It turns out when you apply it, you do the same calculation, but for comparing two different model constraints on the same data, you get basically what's the Bayesian analog of this delta chi-squared over the number of degrees of freedom. So it's basically that, or it's the likelihood posterior average goodness of fit, roughly. And there's a way to turn that into a tension, or tension probability or model comparison statistic, where smaller p-values mean more of a preference for adding the extra parameters. So that's the big overview of what this plot is showing. You can see there's a lot of rows looking at all these different extended models we've looked at. We also look at a couple model variations within Lambda CDM, just for comparison to kind of orient ourselves. So that includes like preference for varying neutrino mass over fixing neutrino mass, or changing our model for intrinsic alignments. We also compare to a couple ad hoc parameters, which are on the bottom, which are parameters that were introduced to explain some odd features of either DES or Planck data. And again, this is sort of, these parameters were introduced specifically to probe tensions between data sets. So we include them here. They're less physically motivated, I would argue, than the models at the top. But yeah, and so the interpretation of each of these statistics is a little bit different, but the main thing, and we kind of highlighted in sort of beige different regions that roughly correspond to 1, 2, and 3 sigma to kind of guide the eye. Or for Bayesian evidence, we've scaled like strength of evidence for the Jeffrey scale. But the fact that we don't see any points sort of towards the top of the plot any further than sort of the lightest beige, except for maybe ineffective, tells us none of these models we don't see more than a 2 or maybe 2.5 sigma preference for extending the model over Lambda CDM. So we consider that to be no significant evidence for beyond Lambda CDM physics. Looking at sort of the Bayesian quantity, sort of the strongest evidence we see for wanting it to add a parameter is this A lens parameter, which, as we said, sort of captures the same features of the CMB data that's driving that sort of omega k or sigma naught tension that we flagged. So this is nothing new. This is something that's been seen in the Planck papers and other analyses. But I guess that sort of gives you kind of a comparison compared to the sort of ad hoc a posteriori parameter introduced to describe this feature of the CMB data. We don't prefer any of the more physically motivated models more. And I guess I missed in the introduction, but the legend's right at the top, where the blue points are for DES alone and black is for the combination of all data. Okay, so yeah, I would say this is one of the like headlines of the paper is we've subjected Lambda CDM to a whole bunch of rigorous tests with very validated modeling, and Lambda CDM lives to fight another day. So since this is, as you said, one of the sort of hot topics in cosmology is discussing the fact that weak lensing surveys or large scale structure probes have sort of consistently been finding slightly lower S8 values than measurements based on the CMB and propagated forward with the expectations of Lambda CDM. We wanted to take a close look at that and how all of these model extensions that we've studied impact that. So this is yet another fairly busy plot, but basically what it's looking at is how different choices of model impact the inferred S8, and we're showing this uh, for a number of different data combinations. So here, particularly the blue band and the red band are marking the locations of the DES only point for Lambda CDM and the Planck only point for Lambda CDM, so the blue and red points in the top row. We've also included, as we have in many of the contour plots earlier, we look at how that changes when we include, BAO, RSD, and supernova with DES, or if we add sort of low redshift geometric probes, that being BAO and supernova to Planck. And then we look at the combination of all data. So if you're sort of looking for the traditional like S8 tension and whether models can alleviate it, you want to be comparing the blue and the red points. But depending on how you think about like geometric degeneracies in the CMB or the behavior of the 3x2 data when you combine with BAO and supernova data, we think these other points are worthwhile to have to add some additional information. So there's a lot to digest here, but I would say that sort of the thing that we have come to after staring at this quite a bit is that none of these extended like beyond Lambda CDM models really decisively, get rid of this offset in sigma 8. Like the dynamic dark energy models, so WCDM and W0WA, do alleviate it somewhat, but not entirely. You do get some movement around with the sterile neutrinos and quite a lot of movement with omega K and the modified gravity, but I'd say for modified gravity, it's a little hard to interpret the separate constraints given the sort of degeneracies between sigma naught and S8. So we're not too concerned about that huge jump in the blue point to the left on the modified gravity row. Um, and again, sort of similarly looking down, we compare to some model variations with Lambda CDM and with those sort of ad hoc parameters, X lens and A lens. And sort of in a similar way to the model comparison investigation compared to just adding this ad hoc A lens parameter, none of the extended models alleviate that S8 tension more. All right, one more, and this is a slide with many points, not necessarily meant for digestion in the talk, but mainly to flag that a lot of the work that went into this project was doing some very careful validation of all of these different models that we've studied. So for the DES cosmology results that came out a year ago, there's a lot of work by a big team to make sure those results are robust, that we understand how different modeling choices influence them. And we're able to, build off of that work. But, when we open up our modeling space to add additional parameters or different software calculations for some of these extended models, we have to revisit some of those tests. So to make sure we could trust the robustness of our results, make sure our results are, to use the cosmology buzzwords, both precise and accurate. We sort of have the systematized approach through the analysis where we made nearly all of our analysis choices based on the analysis of simulated data, where we could make sure that sort of injecting some unmodeled systematics don't shift our results around that much, or if they do, that we can understand what's going on there and change model choices or scale cuts or how we're going to present results accordingly. And then even once we ran on real data, we performed a number of tests, additional robustness tests on our results, changing different modeling choices. And before unblinding our parameter results or model comparison metrics, and we wrote up the whole paper and submitted it through collaboration review and presented on it internally before we knew what the results were to just sort of do some extra checks. So I'll spare you walking through what this plot is, but it's basically an example of something that we use to go through and check robustness to a bunch of different choices that could have been made in the analysis.
Yeah, so one thing first is that we're gonna, like, what's next for, like, just in terms of DES, is that we're still looking at other tests of gravity, like other parameterization of sigma mu and f over gravity. And actually for f over gravity, there are description of the nonlinear power spectrum That will be very interesting to see the results. Um, but again, here another challenge is that we will be using only cosmic shear because anything that's induce a scale-dependent growth, we have to model when we do clustering. So that's also a big challenge we will have to solve. I mean, when I say we, it's like the community, we have to like think about that. Um, then I think like one big milestone will be the results from the 6 years of observation of DES. So that will be like the legacy of DES, and we will do some of those tests of Lambda CDM, and it will be very exciting to see the results then. And then, of course, with the Rubin Observatory, Euclid, the Roman satellites, also there it will be very exciting to see the results. For instance, for Bin Sigma 8, dynamical dark energy, modify gravity with the caveats if we address some of those challenges. And again, another thing as well is that in parallel to photometric surveys, we also have great spectrometric surveys that are coming, like DESI, which is taking data right now. So I think combining DESI and DS would be very impactful to test Lambda CDM even further. And another thing that seems to, a lot of people are thinking more and more about this is to actually go beyond the just, we just summarized the information in the 2-point correlation function, but there is actually a lot of information beyond that. And for instance, there is a lot of information on modified gravity beyond that. So that's also another like path forward in the future.
Yeah, I guess one thing I would add is so there's complementary efforts. I think really just as Agnes pinpointed, to make advances as data get more precise, we really do have to as the modeling end of the cosmology community. We've got to work to, if we think a model beyond Lambda CDM is interesting enough to constrain, we have to like do the work to make sure it's validated enough to use in a real analysis, and that'll only become more stringent as data become more precise. And then sort of complementing that, I would say like models like this bin sigma 8 parameterization, it's not a physical model, but it kind of lets you do a little bit of a consistency test. So that's, I'd say, it's maybe that kind of thing could be a little bit of a stopgap that lets us sort of look for signs of new physics, even if we don't have a particular model for it. But if we detect something there that's not as satisfying as being able to describe the physics behind it. So it doesn't alleviate the need for better modeling at nonlinear scales, but is sort of maybe a little bit of a hacky way to get around it temporarily.